Now, let us go for the next problem. In this problem, we have to show that MZ is a subgroup of Z with respect to the addition operation, where M is some fixed integer. Now let us take one small example here. Suppose I am taking M is 3, then I will have it 3Z. Now what is 3Z? 3Z means I am going to multiply all integers by 3. So 0, 1 multiplied by 3 is 3, 6, 9 and so on. Negative integers, minus 3, minus 6, minus 9 and so on. So this is the set 3Z. Now if you look at carefully, this I can write it as 0, 3 times 1, 3 times 2, 3 times 3 and so on, minus 3 times, so 3 times minus 1, 3 multiplied by minus 2 and so on. So when I am taking MZ, my MZ contains what? 0, M times 1, M times 2 and so on, M times minus 1, M times minus 2 and so on. So this is our set MZ. So I will, for the closure, if I want to check this as a subgroup, the first thing is closure. I will take any two elements from this set. Now how do any two elements of this set look? So I will take arbitrarily, I will pick some two elements, and first element will look like k times m, where k is something like integer, m is our fixed integer, and other element of mz will look like something k times l. Sorry, l times m. So something multiplied by m, something multiplied by m. The k and l are integers, and this m is our fixed integer which we have multiplied to all the elements. So when I start for the solution and when I talk about the closure, I will say that let km and lm belong to the set mz. K and l are integers. What is m? M is our fixed integer. Then what is the addition of km plus lm? Km plus lm is equal to k plus l multiplied by m. So this is again some integer, because k and l are integers, so k plus l is also integer. So this will look like some k dash times m. Then what is k dash? K dash is also an integer, where k dash is actually equal to k plus l. So this means this is also a person which is something multiplied by m. So this element belongs to mz, because mz contains all such elements where something is multiplied by m. So this is also k dash multiplied by m. This means that this element is a multiple of m, and therefore it has to go in the set mz. So this is the closure. So closure holds. Now let us go to the second thing. For subgroups, the second is identity. So here you can clearly guess that the identity of this set mz is 0, because 0 plus any m times k is again equal to m times k, where k is an integer. So this is the identity. The third is inverse with respect to addition. So the inverse, if you take any element km in the set mz, then what should I add to this km so that I will get identity which is 0 back? So what should I add here? I should obviously add here minus k multiplied by m, right? So k is integer, therefore minus k is also integer. So who is the inverse of km? The inverse of km, which is in mz, is minus k times m, which is also some multiple of m. So it is belonging to mz. So inverse is also in the same set. So this means that by our theorem, which says for subgroup, you have to only prove closure, identity and inverse. So this means that by that theorem, I will be sure that mz is a subgroup of z with respect to the operation addition. With respect to addition operation. This finishes our first problem.